Hey everyone, this is Brian. Welcome to week 3 of CSC 143. Hope you had a great weekend and were able to enjoy some of this new, warm, sunny weather here in Seattle. All of your Project Zero submissions have been graded, and you should be able to see your grade now on Canvas. If you also check your submission, you'll see whatever comments I had left for you about your submission and how you might be able to make it better. Project 1 is also out now, and it's something that I can recommend you get started on. Project 1 has a deadline 2 weeks out from the release date rather than just 1 week out, so we get a bit more time, but there's also quite a bit more complexity with the project itself. In Project 1, we're going to explore the relationship between interfaces, classes, and a hierarchy of classes. You will learn about how having child classes substitute parent classes can provide different kinds of child-specific behavior, which we've explored in our last polymorphism lecture. Today's lecture about abstract classes is going to cover a little bit more detail on what you can expect in this Project 1. So once you finish today's lecture, you should have everything you need to know to get started. Project 1 is going to be due on the Wednesday after this coming Wednesday. So you should have plenty of time to get started, and I really recommend you get started early so you have time to think about the kinds of implementations that I'm asking you to do. Before we dive into today's video, I want to talk about the second solid principle reading that I had you do last week, which was the O in the 5 solid principles. We had the single responsibility principle, and now we're on the open-close principle. And the open-close principle tells us that classes are open for extension, but closed for modification. Now that we know how inheritance works, I want us to really start to think about using inheritance to our advantage and using polymorphism to our advantage. The open-close principle is telling us that we should build good foundational base classes and extend them with more specific behaviors and avoid modifying these fundamental base classes for the sake of our child classes. A good example that the paper gives is this shape class that has different kinds of draw methods. One implementation that's offered is a top-level shape, perhaps an abstract class, and it has a draw method that is essentially a giant switch case that knows how to handle every type of shape. It knows how to handle circles, it knows how to handle rectangles, and so forth. This is a violation of the open-close principle because the top-level draw method has to be modified internally every single time we want to come up with a new shape. Let's say we come up with a hexagon. Then we have to go into the top-level shape and modify that draw function to know how to handle a hexagon type. That's not good. We want our base classes to be fundamentally secure and well-designed, but also easily extensible. So the version that it suggests instead we implement is taking advantage of polymorphism and having each individual shape class, like circle, rectangle, or hexagon, that's a child of this top-level shape, override a draw method. That way, this top-level shape can invoke a draw method upon these lower-level shapes, these more specific shapes, and these more specific shapes will have implementations of how to draw themselves within them defined. And there's never a need to actually specifically condition the behavior of the drawing based on the type of the underlying object, because those underlying objects will invoke the appropriate method that their type has defined on them. That is very much the magic of polymorphism, is that regardless of how we are viewing a reference to an object, when we invoke methods on that object, it's always going to go invoke the most specific implementation it has available. So the great thing about that is that we can look at these instances in an abstract way. We can treat them all as individual shapes. We can invoke the draw method upon all these shapes, but the underlying implementations themselves will automatically take place when we invoke those methods without our own intervention. Okay, I think that was a good summary of the O in the 5 solid principles, the open-close principle. I like open-close principle. It really makes you think about using polymorphism rather than kind of hard-coding everything into a top-level God class. So do keep that in mind when you start to design your own classes and your own kinds of class hierarchies, where your top-level classes are base classes that have good fundamental structures that enable these more specific overriding behaviors inside these child classes. Okay, that's all I've got for our intro. Enjoy the show. Hey everyone, this is Brian again, giving you another video lecture for CSC 143. Today we're going to be talking about abstract classes and how they relate to interfaces, which we've already explored. We've discussed abstraction quite a bit in this class already. Abstraction is this idea of masking complexity with simple interfaces. all the classes that we've written so far are concrete. That is to say, they can be directly constructed and have concrete method implementations. An interface, therefore, is not concrete. Interfaces are considered abstract. An interface cannot be literally constructed, and it has to be fulfilled by a concrete class, which is to say that if a class implements an interface, all the abstract method declarations declared inside the interface need to be supplied with a concrete implementation inside the class itself. An abstract class is like an interface in that can also not be directly constructed. Here is a sample abstract class definition. It looks a lot like a normal class declaration, except I put the abstract keyword in front of the word class. Abstract shape is an abstract class and therefore has an optional constructor. Even if that constructor did exist, which it can't actually directly be called because abstract classes can't be directly constructed. Instead, if there is a constructor, it has to be called by a child class that extends abstract shape using the super keyword. That being said, abstract classes are still class definitions. Unlike interfaces, abstract classes can do the following. They can contain variables. They can contain abstract method declarations without implementation, which I suppose is actually quite similar to interfaces. With interfaces, the abstract keyword is implicit, so it's not explicitly defined, but in abstract classes, you can explicitly declare methods as abstract and defer implementation to a implementing concrete class. Abstract classes can contain concrete method implementations, and abstract classes can extend abstract classes as well as implement interfaces. So abstract classes have many of the features of interfaces, like abstract method declarations, but they also have the support of being classes on their own, and that they can have constructors, they can have variables, and they can have concrete method implementations. Let's take a look at how all that behaves. We'll start out with shape.java. When I go to the top of shape.java, it's going to look a little bit different than the shape we've seen in the past. Previously, we've seen shape as an interface. This time I'm declaring shape as an abstract class. I've also said that shape implements the positionable of point interface. Let's actually go take a look at that now to see what that interface obligates shape to do. I'll go ahead and control click on positionable to dive into positionable.java. Public interface positionable, T extends point. Positionable itself is a generic interface, so the generics that we learned last time also apply to interfaces. You may not have seen this keyword extends within the angle brackets before. This is essentially saying that you are permitted to use positionable with any type so long as it extends point. So I'm allowed to declare a positionable that is a generic that applies to the type point or point3D or any other point class that extends from the point. Positionable declares two abstract methods, setLocation and getLocation. So just from observation, you can kind of see that positionable is meant to describe classes that can be located at a particular point. Let's go back to the shape and see how it works. Inside my shape, the nature of shape being a class, means I can declare properties like this string name and this point location, as well as a constructor, which is just the default constructor with nothing in it. Again, though, abstract classes are abstract, like interfaces, they cannot be directly constructed. Just like an interface, methods that are declared abstract have to be implemented by concrete children classes. Here is abstract double area. We've seen the area method declared in the previous version of shape, which we've seen be an interface, but here we're doing it within the abstract class. By nature of this method area being abstract, there's no obligation to actually provide an implementation. In the constructor, we did provide an implementation, it was empty, you can tell by the curly braces, but here, just seeing the semicolon, is a way of saying I'm not going to have an implementation, and I can do that because this is an abstract method. Unlike interfaces though, we're going to say abstract classes can contain implementation that children classes can reuse. For example, let's suppose for a moment that I wanted all my shapes to have names. Among my child classes, I'm going to offer them a free implementation for setName and getName, which are going to do the set and get of the name field as you would expect. these methods, by nature of them being public, are going to be automatically inherited by all child classes. Abstract classes, though, are not obligated to contain any implementation. They may declare all methods abstract. This is even the case for interfaces that the class chooses to implement. Remember how up here we talked about how shape implements positionable of point, and how positionable of point requires a get location and a set location? Well, shape itself is an abstract class. Positionable is an abstract interface by nature. So shape being abstract, implementing the abstract positionable, well, typically we would obligate shape to implement the concrete method implementations for positionable's two methods, but shape being abstract means shape doesn't actually have to do that. Shape can actually ignore the obligations of the abstract requirements of its parents, of its implementing interfaces, because it itself is abstract. We cannot ever directly construct shape, so we can never invoke an abstract method on an instance, because we would have to go find a concrete implementation to do so. So what we find, in effect, is that we don't actually have to make those methods available for us. Here I've gone ahead and overridden them, but if I comment these out, the set location and get location from the positionable interface, we'll see that Java does not complain. Java doesn't complain because shape itself is already abstract. Positionable may have abstract methods, but shape is abstract and says, okay, that's cool, I'll defer the implementation anyway to my child classes. That being said, by nature of shape being an abstract class, it has the option of providing implementation, so we can do so if we'd like, and this would provide this implementation for free to all inheriting child classes. You may also explicitly declare those methods abstract. However, it doesn't really serve that much of a purpose, because the parent methods from the implementing interface, the interface being implemented, already has these method declarations there. This is just one way of saying, I suppose, that if you choose to implement this class, if you choose to extend this class, then you are obligated to implement these interfaces that I have not yet implemented. Let's go ahead and return the concrete implementation here, so that child classes that inherit from the abstract shape can get the positionable interface essentially implemented for free. Much like any other concrete class, abstract classes still inherit from object. Non-abstract methods, like that get position and set position, or I think it's get location and set location, having concrete implementation inside the abstract class is useful for sharing this concrete behavior among child classes. For example, this equals method is automatically inherited from object. Remember that the top level equals implementation provided by object for free isn't particularly useful. All it does is reference equality. By providing an equals implementation inside abstract shape, I can already do some of the basic steps required for implementing equals to compare the internal state of two shapes. If I know that, well, all shapes are reference types, I should go ahead and do all the reference checks, including the class level check, because all classes are going to have to do that anyway. Then I'll go ahead and compare the internal state that I know is automatically shared among all shapes, the name field and the location field, deferring to the equals method for both of those. I put a little note here, don't drop the ball, because I see this pattern a lot and this mistake being made in a lot of programming assignments. It can be tempting to just go ahead and call the equals method on those fields. This.name equals, this.location equals. However, remember that equals, all it does is return a Boolean. It doesn't actually have any side effects. So merely calling the method has no intended purpose. You know nothing, or you gain nothing out of calling the methods because you never save the actual return values from the call to equals. So don't drop the ball. Calling to equals on its own has no effect if you don't utilize the value that is returned from the method call. We can go ahead and do that in one expression with the double ampersand operator that combines this.name.equals with this.location.equals, requiring both to be true. Okay, now let's go dive into some of the concrete implementations, like circle. Class circle extends shape, so it's automatically going to get the name and the location fields, but circle will also go ahead and define its own field, private int radius. We're going to have to define a circle constructor. Here, you might notice that I'm not actually calling the super constructor here, and this is okay because the super constructor is just the default constructor and does nothing. So it's implied inside here that I actually call super, but it's not actually necessary. Looks like I actually have to move it to the very top. There we go. Down here, remember that the area method was declared abstract in the parent abstract shape class, which is going to obligate this concrete circle to define an area method. This is exactly the same in how previously we said shape was an interface and had an area method, and here we have an area method that's concrete and is fulfilling the obligations of the abstract shape. Area is of course pi r squared, and that's going to go ahead and fulfill one obligation. Down here in the equals method, well, the circle class gets equals for free. Equals doesn't actually have to be implemented, and this is actually the case with all classes, right? Because object has an innate equals implementation. But of course, by nature of this class having more specific state than the shape class does, we should go ahead and override equals anyway and make sure that the radius field is compared appropriately. Inside the definition for equals, you should be careful to also make sure to call super.equals. Remember that abstract shape automatically gave me some equals implementation for free to compare the name and the location fields. Therefore, all I have to do inside circle is to compare the new state that's introduced, which is this radius field. I'll go ahead and do that using reference equality because I know radius is a primitive type. Then down here, well, circle is any other class. I can optionally have a toString method that's going to override the default toString. If this class does not actually implement an abstract method that's declared by a parent, just like interfaces, the class will not compile. Class circle must either be declared abstract or implement abstract area method in shape. You can hover over and click on this tooltip to have IntelliJ kind of do it for you for free. It'll give you a stub implementation. Or I suppose we could say circle itself is abstract. Abstract classes can extend other abstract classes. When a class is abstract, it doesn't actually have to provide concrete implementation for any of its abstract obligations, because itself by nature is abstract. The value out of this sort of system is that Java prevents any circumstance where there's a class that's abstract and methods are being invoked that have never been implemented. Because we can never directly construct an abstract class, we can never get in a circumstance where that's the case. Sorry, my cat jumped on the keyboard. Hello, Peaches. Meow. Now let's turn to a different class that also extends shape, rectangle. Just like with circle, rectangle is going to be obligated to implement the abstract methods declared in shape. But also, rectangle can go ahead and declare its own fields and properties. You've got a width and a height. And then we'll go ahead and set up this rectangle constructor. We can even access the properties defined inside shape that are not explicitly shown inside rectangle, because we know that rectangle itself is going to get all of shape's properties. As usual, rectangle can go about defining its own methods, like rotate 90 degrees, which simply swaps the width and the height, get width and get height, and of course override the area method, so that when clients call area, rectangle is going to compute the correct area for the shape. Down here I've got an equals implementation that's got the standard guard statements like the null check, the self check, and the class check. But then I want to show you a sort of anti-pattern with performing a state-wise value comparison among all the properties within each rectangle. As soon as I cast the other object, the argument object, to a rectangle, I can go about comparing all the individual fields within. Notice how I'm going to also explicitly compare the fields that were defined in the abstract shape, the name and the location. I could do this, and this is a valid implementation, but remember that the shape class itself gave me an equals implementation for free. So instead of comparing the name and the location, I could just go ahead and use the superclass's equals method as a shortcut of performing the state-wise value comparisons inside the parent class. Now, there's not necessarily a guarantee that the superclass actually behaves as we would like it to. So maybe there's certain reassurance to doing this sort of check by hand. And of course, you can always go dive into the definition for the parent method and see how it's implemented to make sure it's behaving as expected. But given the well-defined nature of how equals should behave, we can generally expect that the child classes themselves are only really responsible for the new additional fields that are defined within that class, and then we can defer equality for the rest of the class up to the parent. Then down here, I've got a toString method that prints out rectangle and the dimensions of the rectangle. Okay, let's see how it all comes together in the shape test. Let's see, it looks like I have some errors already. Let's try and figure those out. Looks like I forgot to remove the abstract keyword from circle. Let's go fix that. And I need to uncomment out this area method. Okay, let's go back to the shape test. Here we go. Let's go ahead and run everything just to make sure. Great. I start out by defining 2 points, origin and origin 3D. Origin is at 0, 0, and origin 3D is at 0, 0, and 0. My first test, ShapeTest, is going to demonstrate polymorphism in effect. This time using abstract classes on the left and concrete classes on the right. As you would expect, I can fulfill the shape class of reference to a shape using a concrete implementation like circle. So here I've defined the circle wheel with radius of 10 at the origin for circle 1, and a second circle with identical properties for circle 2. Then when I call assert equals, I can expect that circle 1 equals circle 2 by nature of circle 1 having an equals method that implements the value-wise comparison of all the internal fields. Then when I invoke toString, of course we're going to get out the circle-specific implementation of toString. This is, of course, standard polymorphism in action. Java's always going to go figure out what the most specific implementation available is for the particular class. Next down here, I've defined 2 rectangles. Rectangle 1, which is a box, width 2, height 4 at origin, and rectangle 2, which is a rectangle that is a crate, with a width 4, height 2 at origin 3D. Then I go ahead and say assert false that rectangle 1 equals rectangle 2. This of course makes sense because rectangle 1 has a width of 2 and a height of 4, whereas rectangle 2 has a width of 4 and a height of 2. Now, this is always going to call the underlying implementation of equals that's provided by the rectangle class. However, because the references we're using are of type shape on the left-hand side, we don't actually know what the underlying type here is. Even though I suppose we can look at this from the programmer perspective and see that it's very obvious to us. Remember, there are some circumstances where we get a return value that is a shape, and we don't know what concrete class necessarily fulfills that shape. So I can't actually go ahead and call rotate 90 degrees on the rectangle 2 because the nature of the reference itself doesn't actually have a rotate 90 degrees method declared on that type. Instead, I can get around that by performing a runtime type check. We've seen the instance of keyword. We can ask if rectangle 2 is instance of a rectangle, and if that's the case, I'll go ahead and perform a cast on the rectangle 2 reference to turn it from a shape reference into a rectangle reference, and then finally invoke rotate 90 degrees. So I suppose the point I want to make here is Java is going to be smart enough to call the most specific implementation of the underlying instance even when there is a method declaration that's defined in a parent class. And if those methods are matching, such that the child method overrides the parent method, Java's going to go figure out where that child method is and call it. However, when we just look at the reference on its own, we can't go and pull out methods that aren't directly attached to that reference. Java is not going to do that convenient thing for us to go out and try and find this method. Because Java looks at the shape and it says, well, shapes don't have rotate 90, so I can't invoke rotate 90. However, all shapes do have equals, and it just so happens that rectangle overrode equals, so Java can go figure out, hey, rectangle has an equals method. Let me call equals within the rectangle, which is the most specific implementation available by the class. That's why we have to do this runtime check here. Let me show you what the error is if I uncomment out this line. I hover over here, and Java tells me it cannot resolve the method rotate 90 degrees. Okay, let's go ahead and do the rotation and set the name such that rectangle 2 is going to end up matching rectangle 1. I'm going to replace rectangles 2 create name with box. And then I see here that the assertion is going to work. Rectangle 1 does indeed equal rectangle 2, and the toString method is going to behave as expected. Java's going to go find rectangle's toString implementation and call that in place of Shape's native toString implementation. Now let's talk about how interfaces mix in with inheritance and abstract classes. You have to find a public static noop method that returns a positionable and accepts a positionable. The reason this is called noop is because it's no operation. It doesn't do anything particularly useful. All it does is take an argument A and return that same reference on the way out. Now remember that shape implements positionable and circle inherits from shape. Therefore, circle also by nature implements positionable. Remember that the positionable interface simply specifies that implementing classes need a set location and a get location for a generic type that is a point or a child of point. So that back here, circle is a shape and shapes are positionable, meaning I can assign a circle on the right-hand side, a concrete circle instance, to a abstract interface reference, this positionable here on the left. Circle 1 is a type positionable. Other circle is going to be a concrete circle. That's actually a circle reference. And then I'll make circle 2 be a no-op of other circle. Remember, other circle, even though it's a circle reference on the left, a circle type, I'm allowed to call no-op and pass in that circle into the positionable argument by nature of circle itself being a positionable type. Once again, polymorphism in action. I'm allowed to do this because I know that circle, this reference other circle, fulfills all the interface requirements of positionable. However, remember that no-op, the return type itself is positionable. So on the way out, when I call no-op of other circle, I get a positionable type on the way back. No-op is effectively performing a cast here. This is kind of the same as if I put positionable within parentheses and then put it next to other circle here. But I made this method with the intention of forcing you to think about how sometimes when we use method calls or any layers of abstraction, we lose some context of what a reference could be. We went in with a circle and we came out with a positionable, which is a more general type than circle is. Circle is a bit more concrete and specific than positionable. However, the two references are still the same. They still point to the same underlying object. So I may still say assert true, other circle and circle 2 are the same underlying reference. This is still okay even though other circle is a circle type and circle 2 is a positionable type. Remember that when reference equality, when primitive equality is used, Java's going to do a memory address lookup for both of the references. Well, let me clarify that. Java's going to go find the memory address that's stored within the references. It's going to determine what the references are pointing to, and it's going to go match those two arguments together and determine if they're the same underlying memory address. In this case, other circle and circle 2 are literally the same underlying object, this circle defined here, so this assertion is going to hold true, even though the two reference types are a little bit different. Just like we did with rectangle, if I have a more general type on the left, I do have to do a runtime type check to validate that a particular type is indeed a type I'm looking for. If I want to invoke the area method on circle 1, for example, I can't do that because it's by default a positionable, so instead I have to go validate for a moment that it is a circle type, which indeed has the area method, then I can do the cast and then invoke area. A couple things to note here. Technically, if we didn't have this runtime type check, Java would still let us compile. It's kind of weird to think about that Java would let us do that, but remember that Java can't predict in advance how a program's going to behave. So long as it conforms to the laws of polymorphism, Java's going to say, okay, I trust you, I'm going to let you do that cast, and I'm going to let you invoke the area method. However, during runtime, if circle1 fails to be a circle, then this cast will fail, and I'll get a class cast exception. This is why it's always important to do these kinds of runtime checks. This is essentially a guard statement against a circumstance where circle1 is not actually a circle, and Java can't validate in advance how a program's going to behave, so we should go ahead and do that check for certain safety and reassurance that it is indeed a circle underneath. Another point I want to make here is invoking the area method on circle1 has no effect. Remember that all area does is return a double that is the area of the circle. Simply calling the method has no effect. I never save that return value anywhere. I would need to do something like double result is equal to circle1.area in order to take advantage of the outcome of result. This is another circumstance of dropping the ball. Try to avoid doing that. Remember that method calls themselves by nature may not necessarily have side effects attached to them. So you're going to need to save the outcome of that method call for it to be anything useful. So as positionables, the only methods I can invoke on that reference, on those references, are getLocation and setLocation. This can be done without casting because I know those types are positionable and all classes that implement positionable have those two methods available. Interestingly enough, Java is also going to permit me to call equals, even though the reference type is a positionable, because Java knows that all concrete classes are going to have an equals method provided. Here I can invoke getLocation, the equals method on that location, and then getLocation on the other circle. I validate that the two circles are essentially not equal to one another because they're in different locations. If I set location on both circles, they're still not equal to one another because their names don't match. One of them is called wheel and the other one's called round. Then down here, I can go ahead and try doing a set name on the shape itself. Remember that circle1 and circle2 are actually positionable type references, meaning I can't directly invoke set name on those references. Instead, I have to do a runtime type check to make sure that that positionable type is indeed a shape. And well, I know that shape provides a set name, so I can invoke set name on that shape. Finally, at the very end here, I assert that those two things are equal. Looks like I have some leftover code down here. Object array is a new object of 5, array.toString. This is one way of saying that arrays are actually object types, and we can see object methods on these primitive type arrays. This is something interesting to explore, maybe if you have very specific circumstances and you want to use arrays instead of something like an array list, perhaps for performance reasons, but I would say this is mostly out of the scope for this class. So this is kind of a fun fact, but not really related to the stuff we just talked about. Okay, in summary, much like interfaces, abstract classes are going to force concrete behaviors to be defined in a child class. Child classes themselves are either required to implement those abstract methods or be themselves abstract. We saw how we could get away with not defining the area method inside circle by making circle temporarily abstract. Abstract classes are well suited for sharing code among a class hierarchy with distinctive children, but a shared interface and common implementations. For example, all child classes should share a constructor. We saw this behavior with our shape class and how we said, okay, I'd like all shapes to have a name and all shapes to have a location. We can help child classes by having implementation within the top level shape class like equals, which is going to do the work of comparing the name and the positions. But we're also going to force child classes to go provide more specific implementation details. I suppose a real world analogy also works pretty well here. If I asked you to draw a shape, and it had to be in a coordinate grid, well, you would have to fulfill my request with a concrete shape of some kind. It would be a circle, it would be a square, it would be a rectangle, or so forth. So we can think of shape itself as being this abstract entity, this abstract class, but by nature of all shapes sharing some common ideas, the shape itself can also define some concrete implementation details that the child classes automatically inherit for free. Abstract classes that implement interfaces are not actually obligated to provide concrete implementation for the abstract methods of the interface. This is by nature of all methods declared in an interface by nature being abstract, and the abstract class itself being abstract as well. So the abstract class can defer implementation of whatever interfaces it chooses to implement by passing on the responsibility to child classes. When should we use abstract class versus interfaces? It's actually a pretty common interviewing trope to be asked, what's the difference between an abstract class and an interface? In this class, we'll say that abstract classes can contain properties and implementation, whereas interfaces may only contain declarations. Interfaces are sort of simpler. They have a list of methods, and that's about it. They don't provide internal guidance on how those methods are implemented. Abstract classes can have more details. They can have their own internal state. They can have implementation that child classes automatically inherit. They're a bit more complicated in that regard. Classes can only extend a single abstract class, because in Java we have single inheritance, but they can implement several interfaces combined, such as the iterable interface and the comparable interface. We've seen those two interfaces in Project Zero. Interfaces, of course, are mix and match. We can apply any number of interfaces that our class is capable of fulfilling, like comparable, iterable, and so forth. However, we can only ever inherit from one class in Java. One way of thinking about that is that abstract classes live in the class hierarchy. A shape is a parent of a circle, but we don't say like a circle is necessarily a child of the positionable interface. It's not really a child, it's more like it's fulfilling the responsibilities of the positionable itself. So what I mean by that more is if we have several layers of classes, abstract classes can live within particular layers until they start being concrete. But interfaces are sort of transient. They exist outside of the scope of the hierarchy, and classes within the hierarchy can choose to mix and match the interfaces that are available in the global scope. Note that interfaces can extend one another. And it's kind of a fun fact in Java that an interface can actually extend multiple interfaces. And the effect is that an interface is going to combine the method declarations of all the interfaces it chooses to extend as a sort of union interface with all the method declarations of those extended interfaces. However, we're not going to spend too much time exploring that in this class. You may see it in some of the Java documentation, but I think it's simple enough that we can sort of assume that it works well, and we don't have to think about it in further detail. And then, of course, abstract classes, by nature of having implementation, can implement interfaces. The shape class implements the positionable interface, and it can remove the obligation of all of its child classes from also implementing the positionable interface just by providing a default implementation for the child classes to inherit. I do make a note here. In newer versions of Java, interfaces can actually contain implementation. For our purposes, we'll treat them as if they can't. This is another one of those sort of Java fun facts. This is known as a default implementation. You may see the default keyword within interface documentation online. We're going to treat them in this class as if they can't for the sake of simplicity. I like to think of interfaces as just being a list of method declarations so that we don't have to also concern ourselves with the actual implementation inside the interface. There are some circumstances where it is kind of useful, like having a default implementation be readily available that is kind of like a no-op for any child classes, but I think it's a little bit too complicated for us, and in some other programming languages, you're not going to see implementation inside of interfaces, so we're going to treat that the same way in Java. In summary, abstract classes are useful when we want reusable implementation combined with an abstract idea, like the notion of a shape being abstract, but also being useful in that it can contain methods like setName and getPosition. Thinking in interfaces. Perhaps you've seen the ArrayList before, a class that holds a list of objects. ArrayList is an array-like class that supports many familiar operations. you should all be familiar with primitive arrays at this point. If I want to do an assignment onto an index in a primitive array, the equivalent method call in the array list would be the set method for index and value. To retrieve an item out of a primitive array, I can use the get method for the array list, and the equivalent for the length property on primitive arrays is the size method for array lists. However, we should know that arrays are not the only data structure that we can use to store objects. Abstractly, every form of object storage is a collection of things. In Java, the collection interface is just that, an interface providing method stubs for all things that store groups of objects. Let's take a look at the collection interface in collections test. Let's start out with the array list, which should be familiar to all of us. Let's go ahead and run this collections test just in case. But if array list is not familiar to you, that's okay. The interface is pretty simple. Array list is a generic type. Let's go ahead and declare this list X of a type string. I can use the add method to append items to the end of the list, the size method to retrieve the length of the list, the get method to get the properties, or get the value stored at a particular index, and the set method to assign an index with a value. An array list is a kind of collection, and interface is representing a group of objects. Collection itself implements iterable, which we all saw in Project Zero. Here's an example of polymorphism in action with concrete classes on the right, like this new array list, and the interface collection of big integer on the left. This is a collection, therefore it has methods like add. The Java engineers decided all data structures that are collections should have an add method, so I can go ahead and invoke add without knowledge that the underlying data structure is actually a list type. Let's go ahead and put in 0, 1, and 2. And then I can go ahead and retrieve values out of the collection by using the for each loop, which of course applies to all iterable types. Remember that the for each loop is essentially going to go invoke that iterator method to retrieve an iterator for the collection, and then call next until hasNext returns false until the iterator is exhausted to go retrieve individual values outside of the collection. Let's talk about the hash set. A hash set is another kind of collection. We've seen the hash set before when we talked about the sample university class and how we used a set of students to hold those students as a sort of bag of items. Hash sets are a bag of unique items without duplicates according to the equals method. So if an item equals another item according to the dot equals implementation, then hash set's not going to hold more than one of those. Hash set, by nature of it implementing collection, and collection by nature of it implementing iterable, means that collection itself, or hash set itself, can be iterated over using the for each loop, just like we saw with the array list. However, hash set itself has no guarantee of ordering like list. When we do a for each loop over an array list, we're pretty much guaranteed that the values that are retrieved out of the array list are going to be in ascending order, starting with the index of 0. Hash set is not like that. Hash set simply says, okay, I am iterable, but I'm not going to offer ordering guarantees. One way of thinking about this is that hash set is not indexable. Lists can be indexed via the get method, but hash set doesn't have an index. Instead, it's just a bag of items where everything sort of floats around. Let's take a look at how all that works. Let's go ahead and define a new hash set. That's just a collection of pairs of strings and integers. Let's make some pairs, hello world and 1, 2 as my right hand side. I'll go ahead and add hello and world into that hash set. I expect that the size of the set is 2. Then when I try to add hello again, I see that the size does not increase because hash set is going to go figure out, hey, I already have a hello method inside here. Sorry, I already have a hello instance inside here, and I determined that by verifying that I have a pair with the left-hand side being equal to the string hello and the right-hand side being equal to the number 1. I'm going to go validate this by actually building a new instance of pair with a new set of strings and numbers inside that pair, other hello. I validate that hello does not equal other hello, but they do equal each other using the equals method, that value-wise equality. Then I try to add other hello into that set, and I see that the set size once again is not changed. So this is sort of validating that hash set is going to go invoke this equal method that the pair has implemented to go determine if the internal contents of the pairs are the same. It's not going to go do primitive equality, which is kind of silly in these circumstances where we may have multiple versions of the same instance. Then down here, I can go validate that I can indeed iterate over all the pairs within the hash set. However, the ordering isn't guaranteed. This count metric is just to go determine that indeed I'm going to walk this loop twice, because there's two pairs, I'm going to pull out those two pairs inside the body of the loop. Then I validate that indeed the size is correct. So I hope from this little demonstration, you've seen how interfaces themselves can give us valuable information about how we can use these classes without obligating us to understand how the underlying implementation works. When we go about designing interfaces, we should carefully consider what methods should be common among implementing classes. We have to think about what the meaning of the interface is. Collections should have functionality to add, remove, and iterate. Maybe a pets interface should have something like names and species. A buildings interface in some sort of world simulator should have addresses, locations. We're going to see all that come together in Project 1. Project 1 is going to walk through several different interfaces with different purposes in mind, like the building, the store, the supermarket, and the restaurant. And then we're going to need to implement those interfaces to fulfill the different obligations that are required of them. For example, we would expect a restaurant to be a building and also a store. But the restaurant by nature is also different from a supermarket. The supermarket, as we're going to see in the project specification, is going to sell exactly what's in the inventory. Whereas the restaurant is a bit more complicated. The restaurant has to go figure out what items are in stock and determine what recipes can be produced based on the supplies in stock. Be sure to check out the product specification in the Project 1 briefing video for a complete overview of all of these classes. I'll go ahead and omit a walkthrough of these different classes and interfaces in this video because I think the Project 1 briefing has most of that already contained. Okay, that's all I've got for today's notes. Thank you for listening. I'll talk to you next time.